If you want to learn Biot-Savart law and Ampere's law in the quickest way, I recommend you to watch this video. Because they're related, I'll teach you all this at once. I'll be showing every single mathematical step so you can watch it once and understand it all. So if you really want to learn this topic and move on right away, you must at least stay focused when watching this video, okay? I'll go straight to this fact. Use Biot-Savart law to find magnetic field when current is given. So say a rod where current is flowing is given. You have to find magnetic field that's circling around it. You all know that magnetic fields flow around the current, right? According to the right-hand rule. Now, you use Ampere's law to find current when magnetic field is given. So it's the opposite. So this time, magnetic field is given, and you're to find the current. So Biot-Savart law, you find magnetic field using current. Ampere's law, you find current using magnetic field, okay? Alright, let's learn Biot-Savart law. You have seen this formula in your textbook before, right? As I said, current will be given, and you have to find the magnetic field. That's when you use Biot-Savart law. I'm going to first simplify the case by using just a small part of the region. You know from calculus, this D means only a small portion, right? So say we're only focusing on this part of the rod, denoted as DL. This means we're going to think about just this slice of the magnetic field. Imagine you're standing right there, 2 meters away from the rod. This distance corresponds to R prime, which is the separation distance. Now say 125 ampere of current is given. And this portion is 1 centimeter thick. As the current flows, you will start feeling the magnetic field. One person asks you how much magnetic field you feel from that 1 centimeter portion. And we'll try to answer to that. As I said, we'll only talk about the magnetic field generated from this portion of the rod. We wrote it as dB. Now, I'm gonna make small angle approximation to rewrite the formula in this way. What is the difference from our original formula? First of all, R prime is now R. R prime was a variable, but R is now some number. DL will vary the distance in between you and the rod by slightly. But 1 centimeter of variation won't change our separation distance much, right? So even if I have some interval of height, that's why I'm keeping as DL as it is, it's an interval. I'll just assume that this R is 2 meters all the time. That means we just need to find a single value of magnetic field for the fixed R. The original formula had the integral sign, and now we don't have it anymore, right? Because we're not integrating, but just finding a single value for the magnetic field. Now let's look at this equation. You see how we have R arrowed here, down here, but R hat up here. Many students don't notice this, but there's a reason why this one has a hat and this one has an arrow on top of it. In calculus and vectors, we learned that a vector consists of its magnitude and its direction, right? So this one is a vector, but this one isn't any values but just a direction. In our case, you're 2 meters away from the rod, and I said that this direction is the I hat direction, so your vector R should be 2 meters in the I hat direction. Similarly, DL is a vector, so this should be 1 centimeter in the j hat direction, because the current is flowing up, right? So, using this information, I is the 125 amperes, dl was 1 centimeter j hat, r hat is just I hat, so you only plug in the direction, don't bring 2 meters in here, okay? Down below, we have r squared, which means vector r dot vector r. You learned this from calculus. So here we bring 2 meters I hat and 2 meters I hat. This cross symbol is a cross product, not the simple multiplication. I mean, when we were younger, we used this symbol as a number multiplication, right? But you know that this is now the symbol for the cross product. And according to the right-hand rule, A cross B should give this middle finger direction. If our thumb is pointing to j hat direction, and our index finger is pointing to I hat direction, then where our middle finger is pointing at is the answer, which should be minus k direction. So that was just the cross product using the right-hand rule. Now, the dot product here. We can just multiply the numbers first, so 4 meters squared. But this time it's a dot product. And you all know that dot product of two identical directions give unity, 1. So that's also why dot product generates scalar quantities, not vector quantities. In the end, you'll find that the magnetic field is 3.125 times 10 to the negative 8 Tesla in the minus k direction. Okay, we are actually using this cross symbol as multiplication here, I guess. So if you're standing there, and we are only talking about the magnetic field generated from this portion, you're feeling this much of magnetic field in the minus k hat direction. And what is this direction? According to how I define the axis, minus k hat is going into the screen, right? And this totally makes sense. Because if we use this right-hand rule, the magnetic field should in fact be circling in the anti-clockwise direction, right? So, with the current given, we just found the magnetic field using Biot-Savart law. Don't stop the video yet, because it's less likely that this simple case will be on the test. By the way, if you like my explanation, please like and subscribe to my channel. I'll continue now. Now, say you're at this position, so 30 degrees off from this horizontal plane, and you're 4 meters away from this same portion again. By the way, I'm gonna use the same axis, ijk. This time, the vector r should be written in this way. So 4 meters is the magnitude of the vector, and the direction is cosine of 30 degrees in I hat direction, and minus sine 30 degrees in j hat direction. It's minus sine because you went down the horizontal plane, which is the opposite of the j hat direction, right? So if you were up in here, this would have been plus sine 30 j hat. dl is the same. Now this part, as I said, don't get confused. This is a r hat, not the vector r, so there's no 4 meters up here. It's just gonna be 1 centimeter times 1. And for the direction, we have to do the cross product of these two. Because it is no longer perpendicular, we can't use the right-hand rule, but actually do the cross product mathematically. So this cross this. And if you do the math correctly, you'll get negative cosine 30 degree in the k hat direction. So make sure you get the same thing. And plug in the result. Magnetic field is 6.766 times 10 to the negative 9 Tesla in the minus k hat direction. It's 10 to the negative 9, so it's a bit weaker than the previous one, which makes sense because you're in fact farther than before and even off from the plane. Now that we are kind of getting this, let's not just consider the small portion of the rod, but the magnetic field generated from the entire rod. So we'll have to stack the magnetic fields, so this is like integrating it over the length of the rod. So here, I brought the formal Biot-Savart law, which has an integral symbol. We're going to find out how much magnetic field in total this person is receiving from the rod. I have centered this rod on this XY axis. Let's just randomly select a section of the rod. Magnitude of the vector dl is just a dy on the graph. And the direction is along the y-axis, so still j hat. So the vector dl is expressed as dy j hat. Now, our r prime is not a fixed number anymore, but kept as a variable. Because the separation distance will significantly vary now as we take different sections of the rod, this person's position is fixed in x, but the y value will be varied. So r prime could be expressed like this. It's just Pythagorean theorem. And the direction of r prime will keep changing according to this angle, theta, right? So we can express the variable vector r prime as the following. Let's take the cross product and compute this numerator term before integrating. Vector dl cross r prime hat. And again, r prime hat is just a direction. So we are not including the magnitude, which is the square root of x0 squared plus y squared. So I only brought the direction part here. If you do the cross product, you'll see that the j hat term will disappear. And only the I hat term, which has a sine theta, will survive. And in fact, this is related to how we learned that cross product of two vectors is equivalent to the multiplication of the magnitudes of the two vectors multiplied by sine theta. You know that, right? Try it by yourself and see if you get the sine theta dy with the minus k direction. Now, if you look at this triangle, you can tell that sine theta is equivalent to the x naught over square root of x naught squared plus y squared. It's just trigonometry. So we can replace this sine theta with this expression. So this dl cross r prime is done. So if we plug in our expression, we'll get this. Take your time to write all these down. So we got up till here. And let's just simplify a bit. Now, I'm gonna show you how to integrate this. This is just calculus stuff, but I'll show it to you nevertheless, so you don't need to search for the method. We're gonna start by using substitution method. Let y equals to x naught tangent phi. Where is phi coming from? It's from nowhere. I just made it up to do some math. Just follow me through and you'll understand. Then dy should be x naught over cosine phi squared d phi. This is just a derivative. And before I substitute, I want to mention this triangle, which kind of represents this definition. I said that y is equal to x naught tangent phi, so that means tangent phi is y over x naught, and tangent phi is y over x naught, right? Like y is the opposite side and x naught is the adjacent of the triangle. So this triangle will help you understand some stuff later. Anyway, let's replace what we defined for y and dy in the integral. We'll have this. You can check it. Now, 1 plus tangent phi squared, according to one of the trig identities, is 1 over cosine phi squared. You can search that up. So rewriting this, we have this. You can also check that. Now we have x naught squared over cosine phi squared to the power of 3 over 2, right? So we can expand this and get this. Then by canceling the terms, we'll get this. I just took the negative sign out of the integral. Maybe I could have took out this x naught too. But finally, you guys can integrate this, right? It's just sine phi. Now let's talk about this sine phi. Look at this triangle that I mentioned. Sine phi is opposite over hypotenuse, so it should be equivalent to y over square root of x naught squared plus y squared. So we can recover our variable y by replacing it back again. And just by plugging in the final initial value, which was the length of the rod, the total length was 2a. You can go back and check. We'll end up getting this. Again, take your time and make sure you have followed me until here. Because we have successfully integrated it, we have just obtained the total magnetic field generated from this entire rod felt by this person. Congratulations! But don't stop the video yet, not so close. Imagine that this rod is infinitely stretched. So a and negative a is now infinity and negative infinity. As a approaches infinity, this square root term will become approximately a, because x naught is such a small distance compared to a. We can't do much about this x naught outside of the square root because it's a multiplication. But in the addition, this x naught squared for sure won't be significant. So in the end, we'll have this as an answer. As a conclusion, magnetic field near a long straight current carrying wire is simply mu naught I over 2 pi r. That's the end of Biot-Savart law. I hope you're now fully understanding the law. Now, Ampere's law. Ampere's law isn't hard to be visualized. As I mentioned in the beginning, we'll be given some magnetic fields and asked to find its current. You know how we normally draw multiple circles for the magnetic field? So first question could be, when we try to solve this kind of problem, which magnetic field layer should we use? So this is the top view of the magnetic field shown just before. Let's just choose the outermost layer, for example. It's circling around, so it's definitely about a rod. So we could bring this expression for the magnetic field, assuming that we just took the magnetic field layer that is very small compared to the rod. So rod is relatively much longer than the size of the magnetic field layer. By the way, this r is a fixed number because we chose this specific layer, right? It's not a variable, okay? So this expression will be able to come out of the integral later. We're talking about the magnetic field this time, so this vector dl is some small length portion of the magnetic field path. In the Biot-Savart law, dl was the length portion of the current. So this dl and that dl before are the different dl's, okay? Don't get confused. Now, we seem to have a specific type of integral. It has a circle in the integral symbol. This integral is called a contour integral, which means the interval could be rotating on the graph. Dot product gives 0 whenever two vectors are perpendicular to each other, right? So we only care about the case when two vectors are parallel to each other. So we can write it like this. And we are integrating over this circular path, so it's from 0 to 2 pi r, of course. Now, as I mentioned before, this b parallel component can come out of an integral because it's constant. I said r is a fixed value, so everything is constant. So take it out of the integral, and by integrating this, we'll get this 2 pi r canceling with the denominator. By the way, our current is now an enclosed current because our rod should be at the center of the magnetic field that we just integrated. We have just proved the Ampere's law. I'll just end the mathematical explanation here, but I just want to mention that no matter how you make a contour to integrate the magnetic field, as long as our current is enclosed by the contour, you'll always get the same amount of current, as you can see. So that means if your contour doesn't enclose the current, you'll find that the contour integral of the magnetic field is 0. The proof is probably in your textbook, so you can take a look. So, you know what to do now. If I have saved your time, you should like and subscribe to my channel, of course. But I hope this video helped you understand the Biot-Savart law and the Ampere's law clearly. And I hope to see you again next time.